Hi there, in this video we're looking at composing transformations. So doing one transformation and then doing a second transformation and see if we can describe that as a single transformation. So in GCSE, normal GCSE maths, this is the sort of question where they might ask this shape is reflected in the y-axis and then rotated 180 degrees. What single transformation is that? But with normal GCSE, because we're restricted, there's only so much we can do. Whereas here, we can do pretty much any transformation. We can compose them and get a single matrix that represents that transformation. So let's have a bit of a think about what we want to find. So the matrix that represents A then B, we want to be able to write that as a matrix where this first column is where I hat ends up at, and this second column is where J hat ends up at after their whole journey. Yeah, so once we've put I hat through A and then we put that through B, we want this first column to be where that ends up. And similarly, once we put J hat through A and then through B, we want this second column to be where J hat ends up. So a fairly sort of brute force way to do this, I suppose, would be to put I hat and then, so remember, I hat is 1, 0 and J hat is 0, 1. So a brute force way to do it, I suppose, would be to put this matrix into A and then put our answer into B and then see what our answer is. That should tell us what our final answer is. But we don't really need to do that, because if you remember, this guy, if we put it into this matrix here, what happens is, well, 1, 1 is just exactly where I hat ends up after the first transformation A, and 1, 2 is exactly where J hat ends up after this first transformation, after this first transformation A. So let's just sketch what's happening. So we have I hat and we have J hat. We put I hat in and it ends up at 1, 1. And then we put J hat in and it ends up at 1, 2. Okay, so now if we put these two vectors into B, then that's going to tell us what our matrix is. Okay, now remember, because these are sort of applying the transformation, if we're applying a transformation to a vector, the vector always has to be on the right hand side. So the vector has to go there. If it goes on the left hand side, it doesn't make sense. So what we're going to do is, again, remember to last video, we didn't have to just put these vectors in one by one. We can put them in 1 or 2 or 3 at a time. So if we put our I hat 1, 1, and then our J hat 1, 2 into this matrix B, that's going to give us exactly what we're after. Now there's a slightly more concise way to write this. It doesn't really help us with the actual calculation, but the matrix that represents A and then B is just the matrix B times by A. So remember, this is sort of matrix multiplication. If this is matrix B and this is matrix A, we're doing B times by A. Now it's important to note that B times by A might not be the same as A times by B. Okay, you can imagine some transformation where if you reflect it and then shear it, that might be different to if you shear it and then reflect it. So the order of this matrix multiplication really does matter, and we're kind of working backwards almost. A and then B, we're sort of going from right to left, and that's because of this idea that the vector has to go on the right hand side. So if we've got BA and we wanted to apply a vector to it, because the vector's got to come at it from this side, if we want it to hit A first, that's going to be on the right. Then if we want it to hit B second, that's got to be the next thing over. So to work out this matrix, we do B times by A, and then that's going to give us the answer that we're after. So let's work this out. So again, we'll do our working out space. down here, 1, 1, 1, 2. So this one is going to be 2 times 1 and 0 times 1, which is 2. And it's going to be 1 times 1 plus 1 times 3, which is 4. And it's going to be 1 times 1 and 3 times 2 for this bottom one here, which is 1 plus 6 is 7. And then 2 times 1 and 0 times 2 is just 2. So our final answer is 2, 4, 2, 7. Okay, and that is the matrix B times by A, which also represents transformation A followed by B. Again, because a vector's got to approach this transformation from this right-hand side, so it hits A first. So I suppose there's a little exercise for the reader or the viewer. If you want to have a go at finding the matrix B and then A, it's just this multiplication, but the other way around. And I think for this one, you will get something different, sort of just highlighting the fact that it's different. Good. Okay, so on to our next example. So we've got 2 more transformations. We've got A and B, 2, 1, 1, 1, and 1, minus 1, minus 1, 2. And the first thing that we need to do is find the matrix that represents B and then A. And then the second thing we need to do is interpret our answer. So this interpret your answer makes me think that there might be something particularly special about these two matrices. But we'll come on to that once we've figured out the matrix that represents B, then A. Okay, so remember, if we've got a vector and we're applying it to a matrix, we have to come at it from the right. So if we want it to hit B first, that needs to go there, and that needs to go there. So the matrix that represents B, then A, is going to be the answer we get when we do A times by B, using our matrix multiplication method. So A times by B is equal to 2, 1, 1, 1 times by 1, minus 1, minus 1, 2. Let's do some working out space down here. So 2, 1, 1, 1, and then 1, minus 1, minus 1, 2. Okay, so top left one then, 2 times 1 is 2, 1 times minus 1 is minus 1, 2 minus 1 is 1. 2 times negative 1 is negative 2, and then 1 times 2 is 2. Negative 2 plus 2 is 0. Okay. 1 times 1, and then negative 1 times 1, and 1 minus 1 is 0. And then 1 times negative 1 is negative 1, plus the 2 is 1. So A then B is equal to 1, 0, 0, 1, which if you saw the first video, you might recognise as the identity matrix. So this is the identity matrix. So then when it's asking us to interpret our results, and that's what it wants us to talk about. So if we think about the identity matrix as a transformation, well, remember this is where I hat lands, and this is where J hat lands. But if we think back to our diagram, I hat starts at 1, 0, and J hat starts at 0, 1. But I hat ends up at 1, 0, and J hat ends up at 0, 1. This is quite nice because we can think of this identity matrix as the transformation, it's the do nothing transformation. And that's a perfectly valid transformation. I'm going to leave it as transform, I'm going to run out of space. But doing nothing to something is a perfectly valid transformation. It doesn't move it at all, doesn't change the shape, but it is a transformation, and that's what's represented by this identity matrix. So then let's interpret this result instead of A and B. So let's think about what A and B represent. So B, we did the transformation B, so that changed our shape. So if let's say I've got a shape, we did the transformation B, and it ended up as some shape up here. And then we did the transformation A, and we ended back at the do nothing matrix. So B took it from there to there, and A took it straight back again. So that means that A undid what B did. So if, so it's not going to be particularly easy to see these, but if this was like a reflection or an enlargement scale factor 3 and then an enlargement scale factor a third, they undo each other. And there's a special name for this, and they're called the inverse of each other. It's like inverse operations in algebra. Timesing by 3 is the inverse of dividing by 3, because they undo each other. These two matrices are inverse. So okay, A and B are inverse matrices, and because AB is equal to the identity matrix, which we call I. And because AB is equal to the identity matrix I, BA is also going to be equal to that identity matrix. So don't mistake this into thinking that AB is always the same as BA. It's just if they're inverse, then it doesn't matter which way around you times them. Okay, it's good. So that's it for compositions. So a lot of useful information there. And then in our next video, we'll look at how we generalize this further.